Couple of things. The first is that I went through the tangrams in the cabinet the other day, and anybody whose I could find, I gave a grade to. If you didn't have your name written on all your stuff, then I may not have graded it. If you had your name written on some things but not on others, then I graded what I could see, but that doesn't mean that you got full credit for your work. There are some people in here that I couldn't find. I know you had stuff. So Sam, Caden, Eric, I didn't see anything with your name on it. I may have just missed it, but make sure that you get that addressed and make sure that you bring it to my attention so that I can give you a score. If you get a score that you don't believe is reflective of your effort, then check with me, because it's possible that what happened was I just saw part of yours. I know there were some people who made 2, for example, and maybe I saw your first failed attempt and then I didn't find your second really good attempt. For the most part, what I was looking for was effort. We worked on this for 10 days, 5 school days, which means for most of you, I was expecting something more than a piece of wood with some line scribbles on it. You could get partial credit, but if you wanted full credit, what I wanted to see was clear evidence that you were really trying to figure this out and do a really good job of cutting out the tangrams. If it didn't turn out great, that's fine. I wanted to see the evidence of the effort. Yeah?
Are we gonna get the grades uploaded by the end of the day then?
Yeah, I didn't put them in because I knew there were some people who hadn't, I knew that I couldn't find some of them, and so I didn't want to put a bunch of zeros in and startle people. All right, so that's one announcement. The second announcement is I want to just reiterate that there was a point to the work that we did with the tangrams. And what it has to do with is the fact that there is a level of precision that is going to be required for our next activity that is not the same as what we've needed so far. Up until now, it's been reasonably acceptable for you to, I don't know, just kind of eyeball things. So when you were working on your marble machine, for example, if you wanted to make a ramp that was exactly 4 centimeters tall and 5.3 centimeters long, and then you built it, and it ended up being 3 centimeters high and 4.5 centimeters long, who cares? It doesn't matter. Nobody will know the difference between what you built and what you wanted to build. Even to the point of, some of you did, and I can see this on this little piece of scrap that I made. I just took one of these pieces of wood and just broke it in half by hand. It was so thin that I just snapped it in half. I didn't even cut it. We are gonna spend much of the rest of the school year making musical instruments. With musical instruments, it's really different. Now, some of you may decide that you want to make a stringed instrument like a guitar. That's okay. But if you're gonna do that, you're gonna have to be incredibly careful. Because if you look at a guitar, one of the things that you'll see is these metal bars, which are called frets. They're arranged in such a way that they become less and less far apart as you move from one end of the guitar to the other. And that is what accounts for the notes. If you don't measure and calculate and put the frets in exactly the right spot, you're not going to be able to make chords. The notes won't be right. You can't play a guitar if the frets aren't in the right spot. It just won't work. And there's all sorts of other things too that have to do with really precise measurements. One thing that you won't need to worry about is the strings, because you're not going to manufacture those. If you want to make a stringed instrument, you'll buy the strings. But again, if you look at these strings, you can see that some of them are bigger and some of them are smaller. And that size difference is not just random. People didn't just well, let's just make this one a little bigger or a little smaller. It turns out that if you want the right notes, you have to have the strings the right size, you have to have the frets in the right spot. Most of you, when you make your musical instruments, are gonna probably try to make something that is the equivalent of like a xylophone or like marimbas, where what you're gonna do is you're gonna use pieces of wood that resonate at a particular frequency, so it makes a note. If you don't cut the piece of wood the right size and shape, you're not gonna get the right notes, right? And so we have to have the size and the proportions of the things that we do have to be as perfect as we can make them. The whole reason we did the tangrams was so that you could practice doing that kind of work. The tangrams kind of defeated many of you, not in a bad way. It defeated me too. What I found was that unless I used the table saw, which is something that you all have not been checked out on, I couldn't really get my tangram to look the way that I wanted it to. But I learned a bunch of stuff. And not today, but next week, I'm gonna share with you some of the things that I learned and some of the suggestions that I got from you. Ms. Reinwald had some really good insight. What I hope is that we can take all the successes and all the failures that we had collectively with making the tangrams and turn that into knowledge that we can use to make musical instruments. Ideally, and this is a tall order for the first time that you've done something like this. Some of you, this isn't the first time you've done something like this, but if it is, this is gonna be a big challenge. But ideally, you would leave here, the end of the school year, with something that creates music, that is like a work of art, and that you're really proud of. The work that we need to do going into that is both on the skilled side, the woodworking side, and on the calculation side. You just cut a bunch of pieces of wood and hit them with a hammer. You're not gonna get what you want. So before we can really think about the specifics of how we're gonna build the musical instruments, we need to figure out a little bit about sound, what sound is and how it works. So I'm gonna just go through with you today the idea of sound as a wave through air and how we can think about the differences in waves accounting for the differences in the sounds that we hear. And some of the work that we do today is just gonna be a demonstration. I'm gonna show you some waveforms so you can kind of see what it looks like. But some of the work that we do, you're gonna do. You're not gonna be able to see the waveforms, but you're gonna calculate a really important part of sound waves. It's been a while since we've been in here and I've written stuff down, so I just want to remind you that if I underline it, you should write it. If I draw it, you should write it. But I don't expect you to make perfect copies of the diagrams that are up here, but you might make little sketches too. So a wave is something that we use to refer to a bunch of stuff. Light is a wave, sound is a wave, electromagnetic radiation is a wave. We see waves in water. We wave our hands. All of those waves have in common the idea that it's a repetitive disturbance in something. If you have a hand like this sticking straight up, there's no disturbance. If the hand moves around, it's a disturbance, right? The hand is being disturbed. If you move that hand back and forth, then you have this repetitive, predictable disturbance. And sometimes that's called an oscillation. That's what waves look like. Sometimes we can see waves like ripples on the water. Sometimes we can measure waves like we have, you'll see this today. We have equipment, tools, apps, and physical devices that can take things that we can't see and turn them into waveforms that we can see. Yeah?
Like earthquake?
Earthquakes are waves, that's a great example, yeah. So a seismograph is a device that takes the shaking that we feel and it turns it into waveforms on a piece of paper. And one of the interesting things about waves is that we can characterize them in a bunch of different ways no matter what they are. Whether we're talking about light or sound or ripples in a pond or earthquakes or somebody's hand going back and forth, they all have some sort of basic measurements. One of the measurements is frequency. That's how quickly the wave repeats over time. So if you see a wave like this, you can see that it's like if you imagine this wave moving moving, you can imagine that we're not getting very many waves in a certain amount of time. Like if you counted 1 or 2 seconds, we wouldn't see that many waves. But here, we're seeing a lot more waves, okay? So frequency, if you think of your hand, and like the motion of your hand is the wave, like here's a low frequency wave. We're not getting very many waves in a unit of time. This is a medium frequency wave, and this is a high frequency wave, okay? The faster the wiggling back and forth or up and down goes, the greater the frequency. We'll look at that more later on. For now, just understand that it has to do with how quickly the wave is wiggling, and it's something that's fundamental to a wave. Another thing is amplitude. That has to do with the size of the wiggles. And so this would be a low amplitude wave, and this would be a higher amplitude wave. You can change amplitude without changing the frequency. So I could have 3 waves per second. 1, 2, 3, 1, 2, 3, 1, 2, 3 at a high amplitude, or I could have 3 waves per second at a low amplitude. Okay? And amplitude is often depicted by the height of a wave if we draw it, right? So in a ripple on a pond, the height of those waves would be the amplitude. If you're at the beach, the height of the waves would reflect in some way the amplitude. And with sound waves, well, the amplitude isn't the height really, because sound waves don't have height. But when we draw sound waves, we draw them like this. And so the amplitude would mean bigger, taller sound waves. And then the last thing is wave speed. And that's weird because it seems like the speed would be how quickly my hand is moving back and forth. But that's not wave speed. So it turns out we can have 2 kinds of ways that we think about waves. One is like this, where the wave itself isn't going anywhere. My hand is, but the wave is in the same place over and over and over and over again. The other way that we can think about waves as something that moves. In that case, the hand going back and forth, in this case, which is the wave, isn't changing at all, but the location is. So if my hand moving back and forth is moving in a certain direction, then it has a wave speed. And how fast it's going is measured the same way that we measure the speed of anything else, in meters per second. So a slow wave speed would look like this. A fast wave speed would look like this. My motion left to right is the wave speed. The motion of my hand is the frequency. Those are independent. We can have a really fast frequency at a really slow wave speed. We can have a really slow frequency at a really fast wave speed. And it gets confusing because typically with waves, they're sort of repeated. So typically, we don't just have one hand moving back and forth, but we have a bunch of hands. So at any one time, if you look, you see a hand waving. It kind of doesn't look like it's moving, but it's a different hand. If you look at my hands as they move, and imagine that there were like 7 Mr. Bregars here. We were all standing next to each other, moving our hands back and forth like this. You can see the wave is moving. If you were to look at this spot right here, you'd always see a hand going back and forth. First it would be my left hand, then it would be my right hand, then it would be the next Mr. Bregars' left hand, and then his right hand, and then the next one, and then the next one, and then the next one, and then the next one. That's all these things right here, right? These are all like Mr. Bregars, and they're all waving back and forth. And they have a frequency, how quickly the wiggling is, and they're moving in one direction or another. That's the wave speed. If we see a wave, it's a lot easier to see the frequency and the wave speed, right? Because the frequency is the wiggling back and forth, the wave speed is the motion one way or the other. But a lot of times we can't see it. when we think about sound waves, which is what we're really gonna be working with, those we can hear. We can hear the frequency of sound waves. When it comes to the speed, well, we'll talk about that in just a second. And one of the things that's kind of cool to think about is that what's really going on with a wave is that it's transferring something called energy. We probably won't have time to talk about what energy really is, but we can think about it as like how powerful something's motion is. So if there's just a little bit of motion over here in a wave that's moving from your left to your right, then that motion energy is being transferred as the wave moves. Yeah?
So what exactly are we gonna work on today that relates to weight?
You'll find out. That's a great question. So, yeah.
I don't know if you thought of this, but a great project for something like this is making a seismograph out of string and a piece of paper and having like a wave cable.
You're absolutely right. And we could do that. We're gonna focus on sound waves, but if you wanna build something else, I would love it. Like you could so easily, I mean, a seismograph is a very basic piece of equipment. It has to be precisely engineered, but it doesn't require like fancy technology. Like you don't need, there doesn't even need to be any electronics really. Like you can make a seismograph with a hand crank and yeah, like you said, a sort of a pendulum pencil. So yeah, there's lots of ways that we could look at this. We're gonna look at sound. And sound waves are waves in the air. We can't see them because air is invisible, but air is made up of tiny little particles called air molecules. Sound can go through other things as well. You probably have gone swimming and heard sound underwater. You've also probably heard sound in other things as well, like if you have your ear up against a door and you can hear stuff from the other side of the door, those sound waves aren't coming from air, it's the door itself vibrating. Any vibration can be potentially interpreted as sound. But most of the time, our ears are in the air. So most of the time, the vibrations our ears pick up are vibrations of air molecules. And it's a wave, but it's a different kind of wave than like ripples in a pond. With ripples in a pond, you kind of see this up and down thing. We're surrounded by air, it's three-dimensional. Sound is what's called a compression wave. The air molecules don't go up and down. They go back and forth, and sometimes when they go back and forth, they're closer to each other, and sometimes they're farther away from each other. So if we could see sound, if we could see it, we wouldn't see it as swoopy waves like this. We would see it as bands of air that are closer together and farther away, closer, farther away, closer and farther away. If we could see this moving, what we would see is these bands kind of moving back and forth, vibrating, and moving to the right. There would be a wave speed, that's how quickly the whole thing is moving one way, in one direction, and there would be a wave frequency, which would be how quickly they're vibrating back and forth. Both of those things are important when it comes to sound. When it comes to the speed, the wave speed, how quickly this back and forth wiggling goes between a source of sound and our ears, it's always about the same. And your job today is going to be to figure out how fast that air moves. Okay, so we're going to try to figure out, our goal today is going to be to figure out the speed of sound. And the last thing that I want to show you is something, we'll come back to this down the road. The speed of sound determines how long it takes a sound to get to your ears. The frequency of a sound determines its pitch. And you can hear that pretty clearly. So I'm going to use my phone here because I have this tone generator set up. Of course it's not working because I don't have anything on this phone. I don't know how anybody uses honestly, this is the worst device I've ever owned. The only thing iPhones have going for them is iMessage. Everything else just never works the way that I would expect it to.
Like the charge.
Look at the camera.
Huh?
Great camera.
Yeah, well, it's just, I mean, every phone has a great camera. Here we go. Okay, here's a tone. Hear that? If I change the frequency of that tone, you'll hear higher or lower pitches. Higher pitches have higher frequencies. Lower frequencies have lower pitches. If we change the amplitude, we change the volume. Same pitch, lower volume, higher volume. And here's what's kind of interesting. We can measure these and we can combine them. So let's take a look at what that looks like. Okay. Okay, there's one tone right there, just kind of frozen it. This has a frequency of 431 wiggles per second. If I increase that, now that's a frequency of about 760 cycles or waves per second. And here's where it gets really neat is we can combine these. So I have to refresh all of these because, you know, it's an iPhone.
Be nice.
Well, I don't have to be nice to my phone. It's not all that nice to me. Okay, so you can actually, by the way, you can see my voice, right? Like that's kind of a crazy, my voice is just a sound wave. But here's what happens when we combine sound waves. So here's a 440 wiggle per second sound wave. And I can combine that with a 760 and I can combine that, I know it sounds terrible, doesn't it, with a 295.
You like 1,000?
And look what happens to the wave. It gets all like weird. The more frequencies we add to our wave, the weirder it looks. That's why my voice, even though my voice is just one single wave, it has all this craziness. There's low frequencies mixed with high frequencies, mixed with really high frequencies, mixed with medium frequencies. They're all mixed together. And it's this crazy mixing together that makes like what we think of as sound. It's just one wave. It's just one, like moving like this with various wiggles. But all those wiggles kind of combine. You get these particles moving back and forth fast and slow, and they like bonk into your ear, and then your ear takes it all apart and hears different people's voices or scissors or pencils or guitars or, you know, drums or whatever. It all combines in our ears and then our brains take it apart. It's nuts. Sam?
Can we do like 1,000?
What's that?
Can we do one like
Sure, yeah. So 1,000 isn't that high pitch. So some of you may know that I like to play music, and so I have a reasonably good sense of what these different pitches sound like. So 1,000 is this.
Can we do more? Can we go like 2,000?
That's 1,000.
Like
A really low pitch, about the lowest pitch our ears can hear is about 20. So my phone can't really make it. Like this is 50. You would be able to hear this if this were a real speaker, but there's about 160. Most of you can hear that.
That hurts.
Y'all shut up.
And then as we get higher and higher and higher, what you'll find is some of you probably can't hear it. So here's a dog whistle pitch. Here's even more. Even more, sorry. And one of the things that's really interesting and kind of fun you can do this online, is to do a hearing test. Those of you who like to listen to really loud music have probably already damaged your hearing permanently. I like to listen to loud music, and I have damaged my hearing permanently. I have what's called tinnitus. My tinnitus is somewhere between 3,000 and 6,000 wiggles per second, which means I constantly hear that, like the same noise that was driving some of you crazy, I hear that all the time. It's just stuck in my head. It's not super pleasant. There's nothing I can do about it. It's not fixable. One of the things that's kind of interesting though is, despite that tinnitus, I still can hear well up into the tens of thousands of wiggles per second. I can hear really high pitches. I just have this like high-pitched noise that's always there in my head. And so, you know, when I was your age and older, I just didn't care because I thought, well, it's not bothering me now. And this is one of those things where it's like, man, if I could, I would go back and I would wear earplugs at concerts, where I played in bands for much of my life. I never used to wear earplugs. We'd go to these band practices and we were just like super loud. And I wish I hadn't have done that, because now I have to deal with this 100% of the time. Yeah?
I don't have like the ringing, but like I can't hear as good as this year because I used to like I always had like an earbud in and I was blasting.
Yeah.
And ever since I was like tiny with my little
Yeah.
and stuff, so
Yeah.
now like if I cover this ear, it's like really
Dull.
soft.
Yeah.
it sounds-
So you are likely to never get that back. It's possible that that at some point in the future we will develop some treatments. So it's possible that we may be able to fix that. But as of right now, we don't have anything, and there's not even anything in sight. We can't stop the ringing, and we can't bring back hearing loss. So I don't know. Take it for what it's worth.
What if you just like deafen yourself and give yourself like hearing aids now?
So if you get hearing aids, and if you know anybody with hearing aids, you should ask them about it, because what you'll find is hearing aids are not nearly as good as undamaged hearing. They just aren't. It's better than nothing, right? Like if you are really losing your hearing and you get a hearing aid, it can really help. But if you compare your hearing with a hearing aid to your hearing before you had any damage, there's no comparison. You all right now you have the best hearing you're ever gonna have. It's never gonna get better. It might get worse, even with a hearing aid. There's no way that you're ever gonna have better hearing than what you have right now. So think about that. I would advise you not to listen to music that's so loud. One of the fun things about loud music is that you can feel it, so get a pair. Some of you don't have much money, and I get that, but everybody can afford these little foam earplugs. These things are dirt cheap. You can even get them for free in many places. These are worth having. I carry them around wherever I go. And if you can afford it, get really good earplugs. If you get really good earplugs, it's like turning down the sound on everything, but it doesn't change like the different frequencies, so you can still hear real high frequencies and low frequencies. And then you can crank your music and feel the bass, but it's not really that loud in your ears. That's the best solution. Yeah.
Do you have like these, like AirPods?
AirPods can help. Yeah, I use my AirPods a lot for that, and I set them up. I put them with the adaptive noise cancellation, and like, yeah, that works pretty well. I have not used them at a concert though, and
I mean, they stop like AirPods, so I've shot guns with them in my ear.
yeah. So I believe you. What I don't know is whether there's something called a transient, which is a loud noise that can kind of get through any kind of electronic device. I don't know if these allow transients through or not, and if they do, sometimes you can't even hear them, but they cause damage anyway. So I wouldn't count on them unless you looked it up. If the noise cancellation on earbuds has been shown to reduce hearing damage and hearing loss, that's awesome. But I wouldn't count on that unless I saw that research. Not right now, but in a few minutes, yeah. All right, so here is what we're gonna ask you to do today. So we talked about the idea that sound is a wave, wiggles back and forth. The faster the wiggles, the higher the pitch. That wave also moves, the whole wave moves, that's the wave speed. It turns out that in air, sound will move at the same speed all the time, no matter what the frequency. And if it's real warm, or real cold, or if it's real humid, or real dry, it can change a little bit, but not dramatically. Not enough that we would notice it with our ears. It is dramatic enough that we can feel it if we're singers. If you're a singer, you change the way that you sing, depending on the air temperature and humidity. And if you play any instruments, how many of you play instruments? If you've ever played your instruments on like a cold day versus a warm day, you may notice that stringed instruments can go out of tune. Or like wind instruments. Like if you play saxophone and you get your saxophone all tuned up backstage, and then you go out into the like hot, humid club, you have to tune it again. Same with guitar. And even drums are the same way. Like you cannot keep an instrument in tune if you put it in a slightly different environment. That's just how it works. But mostly the speed of sound is always the same. Speed, as you all know, is distance divided by time. So we need to know, if we want to know the speed of something, we need to measure how far it goes and how long it takes to get there. And we have a relatively simple challenge to put before you today, which is we want you to figure out how fast sound moves through the air. It's simple in the sense that it's easy to express. What is the speed of sound? How quickly does wiggling move from one point to another? How fast is the sound of my clap going from my hands to your ears? How quickly did that compression wiggly wave move from its origin, which is right here, out to you? The problem is, if you want to measure how far something goes and you can't see it, what do? Right? Like I can tell, like, we know how far it goes. Like if I were to try to figure out, well, we want to figure out how far the sound goes, so let's measure how long it takes to get from me to Cole. Ready? How long did that take?
I heard it instantly.
Okay, so that's not going to help us. You heard it instantly. You didn't, but you think you did.
Well, yeah, it's very, very. But you can tell
Yeah.
as
So we
it gets
can't
further
quite
away.
do it. You can't quite do it the same way that you would with like a tennis ball or something like that. Yeah.
Don't scientists like use sound waves to measure certain lengths in space because you
Yeah.
can't really see things?
Yeah, so since we know how fast sound moves, if we bounce sound waves off of things and measure how long it takes for those sound waves to come back to the source, we can do some math and figure out how far away they are. We did that in this class. Phoenix, you weren't here. But we did remember, yeah, it's echolocation. Remember the motion sensors that we used? Those are sonar. That's why you could hear a little click, 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 every time we turned them on. It was measuring how far something away was by bouncing a sound off of it. So that's effectively what we're gonna do. But it's not gonna work in here, obviously. So we're gonna go outside to do it. And here's what we're gonna ask you to do. And this is all on Canvas, but I'm gonna go through it really quickly just so everybody has an idea. And your goal is to get it as close to accurate as possible. You could look it up, but that doesn't count. I know what it is. Ms. Reinwald will know what it is. Mr. Laxton will know what it is if they don't already. We want you to figure out how you're gonna do it. The only equipment we have for you is stopwatches. That's it. That's all you need. So, step one, you're gonna work with one other person. No groups of 3. If you wanna work by yourself, you can't, because you need 2 people to do this. Actually, that's not entirely true. You can do it with just one person. If you wanna work by yourself, that's fine. If we have an odd number of people in here, then one of the 3 of us will work with you. No groups of 3. It's not a 3-person thing. And then, before you go outside, figure out exactly what you're gonna measure. And talk to either me, Ms. Reinwald, or Mr. Laxton. If you can't explain exactly what you're gonna measure, and exactly how you're gonna measure, we're not gonna let you go outside. Once you've figured out the measurements you're gonna make, go collect data. And I want you to make a data table that has room for 10 trials of your measurements. So that means it's gonna look, I don't know what measurements you're gonna make, but it's gonna look something like this. You're gonna have 10 trials that you do, and then you're gonna have some measurement that you're gonna take, and some other measurement that you're gonna make, and some other, I don't know how many you're gonna need, but 2, 3 measurements maybe. And each trial, you're gonna make those measurements. Once you've got that data collected, then you'll come back in and do a calculation. Most of you are gonna be making the same kinds of measurements. Most of you are gonna use this equation right here. Speed equals distance divided by time. That's the key. For things that are moving at a constant speed, which sound is, then if you can figure out how far it goes, figure out how long it takes to get there, then you can just divide those two things. We want our times to be in seconds, and we want our distances ultimately to be in meters. Now, you may not measure in meters at first, we can convert later. But in general, in this class, we've talked about meters per second as being sort of our standard measurement of speed or velocity. So we want our velocities to be in meters per second, which means your distances are going to be in meters, your times are going to be in seconds. If you measure in something else, that's fine, but what you'll need to do is kind of do some conversions later, and we can help you with that. And then once you've got your calculations done, see what other people got, and then check with one of us, and we'll tell you how close you are. If you're really, really, really close, and you got really, really good consistent data, that's pretty great. Most likely, what you're gonna find is your data isn't consistent, and the calculations between groups aren't super consistent either. There's a really easy way to solve that problem, but it's gonna require you all to work together. So after we've taken our first measurements and gotten our first set of data, we're gonna try again, and we're gonna approach it a slightly different way. We're gonna let you kind of piece it together, but there's gonna be a way that we can work together as a group to get a really, really good estimate of the speed of sound, okay? All right, so does anybody have any questions? Yeah?
Could people use like a meter stick to do 1 meter? To measure
Yes,
out the
theoretically, but what you're gonna find is, in practice, that's gonna take forever. And the reason is because, like we just discovered in here, this isn't far enough for us to measure an amount of time. So you're gonna be so far apart, that's why we have to go outside. You're gonna be so far apart from the other person that measuring your distance with a meter stick is not gonna be practical. Even a meter tape is probably not that practical. We're gonna go out to the track. Why are we going out to the track? What's the advantage of measuring out at the track? Yeah?
It has measurements.
We have the measurements on there already. So we can measure distances really quickly by going out to the track, okay?
But there's only like a couple distances measured.
That's true. There's ways that we can work around that
Yeah,
though.
most of them are straight.
That's,
Not most of them are, most of them aren't straight.
that's true, but we can work around that too. There's lots of ways that we can approach this, yeah. Sound doesn't go in a circle, so we gotta stick on the straight parts, yeah.
Yeah, so it's just the 100.
Yeah. Okay, any other questions? All right, so before you go anywhere, we wanna see your plan with your partner. We wanna see that you have a plan and that you know what you're gonna do, how you're gonna measure stuff. And then once you have gotten checked off by one of the 3 of us, you can head out to the track and we'll come out there too, or I will.